In 2025, China launched more ships than the rest of the world combined. Not by a little, by more than double. And right now, nearly 70% of every new ship being ordered anywhere on the planet is being built in China. That means the majority of ships that will carry the world's oil, gas, and cargo for the next 30 years have already been designed, ordered, and are being built right now in Chinese shipyards. We're talking about these oil tankers that are so massive that 3 football fields fit inside their length, so tall that their engine alone stands as high as a 4-story building, and so powerful that a single voyage carries enough oil to meet 10% of America's daily consumption. Ships that carry enough oil to power entire countries for days, and the US is watching all of this very, very carefully. The real question isn't whether China is winning the shipbuilding race. The question is, how did they get so far ahead that the race is basically already over? And more importantly, what does that mean for the rest of the world? Because this isn't just about ships. It is about who controls the flow of energy on this planet. If this sounds like something you want to understand fully, hit like and subscribe right now, because this is exactly the kind of story we dig into on this channel. And by the end of this video, you'll see the ocean very differently. From 3 giants to 1. For decades, shipbuilding was a competition between 3 countries: Japan, South Korea, and China. Think of it like a 3-legged race, where each country had its own strengths. Japan had the experience and the precision that came from generations of craftsmanship. South Korea had cutting-edge technology and a reputation for speed. China had the scale, the workforce, and the hunger to grow faster than anyone expected. The rest of the world, especially Western nations, watched this dynamic and felt comfortable. As long as those 3 kept competing with each other, no single country could grab too much control. It felt balanced, stable, safe. And for a while, it was. But here's what nobody saw coming. China didn't just get better at building ships. It went back to the drawing board and rebuilt the entire system around how ships are made from the ground up. It didn't play the same game better than everyone else. It changed the rules of the game entirely. And once you change the rules, the old scoreboard stops mattering. By 2025, China was producing 53.69 million deadweight tons of ships in a single year. That number represents more than 56% of everything built on the entire planet. South Korea, which used to be neck and neck with China just a decade earlier, was watching from a significant distance behind. Japan had fallen even further back. The 3-legged race had quietly become a solo sprint. But the order books told an even bigger and more striking story. Nearly 7 out of every 10 new ships being ordered anywhere in the world were going to Chinese yards. That's not just market share, that's a preview of the future. The global fleet of 2040, 2050, the ships that will still be sailing when today's teenagers are middle-aged, is being shaped in China right now, today, while you're watching this video. When you control what gets built today, you control how the world moves tomorrow. But to really understand the weight of that, you first need to understand what these ships actually are. Because we're not talking about anything you'd picture when someone casually says the word ship. A ship bigger than you think. A very large crude carrier, which people in the industry simply call a VLCC, is one of the biggest moving objects ever created by human hands. We're talking about a vessel that stretches around 330 meters from one end to the other. That's longer than 3 football fields placed end to end in a straight line. Its width runs about 60 meters across, wide enough that you could lay a multi-story building horizontally across the deck and it would fit comfortably. It carries around 2 million barrels of crude oil in a single trip. To give you a sense of what that actually means in the real world, the United States uses about 20 million barrels of oil every single day. One of these ships carries roughly 10% of that in a single voyage. One ship, one trip. The steel alone that goes into building a single VLCC weighs about 55,000 tons. If that number doesn't mean anything to you yet, think of it this way. That's roughly the same weight as 7 Eiffel Towers stacked together. And every single plate of that steel, every cut, every weld, every joint across that entire mountain of metal has to be close to perfect. Not good enough, not nearly right, nearly perfect. Because the ocean doesn't forgive shortcuts. The waves of the North Atlantic can bend steel beams. Pacific storms have swallowed ships whole, and inside the hull, 2 million barrels of crude oil doesn't sit perfectly still. It sloshes, it surges, it slams against the walls with every wave the ship passes through, creating internal pressure that shifts constantly and beats on the structure from the inside out for decades. A ship like this has to survive all of that continuously for 25 to 30 years. And somehow, China can build one of these from raw steel plates to a sea-ready vessel in under 2 years. When you first hear that, it sounds impossible. But once you see how they actually do it, it sounds almost inevitable. And that's exactly what we're going to break down right now. The ocean imposes one rule above everything else on every ship ever built. It doesn't matter how big you are, how expensive you were, or how advanced your technology is. If your structure fails, you go down. That principle, the idea that every single design decision is ultimately about survival, is where China's shipbuilding philosophy begins. The hull of a VLCC is built with 2 layers of steel separated by several meters of space between them. That gap acts as a buffer zone. If the outer shell gets hit, pierced, or cracked, the inner layer holds. It's a passive defense system, but in an environment as unforgiving as the open ocean, passive defense can mean the difference between a near miss and a catastrophe. Inside the hull, the space is divided into separate compartments by walls called bulkheads. These aren't just storage dividers. Their job is to control the movement of that liquid cargo, to limit the sloshing and surging that would otherwise create dangerous shifting forces inside the ship. The walls that hold the oil don't just contain it, they manage the physics of it. And then there's corrosion. Seawater is one of the most destructive substances on the planet when it comes to metal. Salt, moisture, and chemical compounds attack steel constantly, eating through it slowly and invisibly over time. To fight this, the interior storage tanks are coated with multiple layers of specialized epoxy, a chemical shield that sits between the steel and everything that wants to destroy it. Every feature of these ships is built around one idea, not optimization. Survival first. And only once survival is guaranteed does everything else get refined. That philosophy carries directly into the way these ships are built, which is where things start to get genuinely fascinating. The factory that never sleeps. Let's start with the steel cutting, because this is where the entire process either succeeds or fails before the ship even begins to take shape. Every one of those 55,000 tons of steel plate gets fed into massive computer-controlled cutting systems. Every single cut is pre-programmed. The machines work with a precision that doesn't allow for even a quarter inch of deviation. That strictness isn't perfectionism for its own sake. A small error at the cutting stage doesn't stay small. It travels forward through every step that follows. When thousands of pieces need to fit together later, a quarter inch off on one plate becomes a centimeter off on an assembly, which becomes a structural weakness in the finished hull. By the time you find the problem, you're not fixing a cut, you're rebuilding a section. So the standard has to be near absolute from the very first moment. Now here's where the real innovation kicks in. Instead of building a ship the traditional way, starting from the bottom and slowly working upward, one layer at a time, in a process that used to take 4 or 5 years, Chinese engineers broke the whole thing apart mentally first. They take the blueprint of the ship and slice it into more than 100 giant sections on paper. Each section weighs between 300 and 600 tons. Then they build each section completely separately, on the ground, adding pipes, electrical wiring, and protective coatings, before it ever gets attached to the main structure. Then, massive cranes pick these finished sections up and lock them into position like the world's biggest, most expensive jigsaw puzzle. This method is called modular block construction, and it's the same kind of thinking that aerospace engineers use when assembling rockets and satellites. The core idea is simple but revolutionary. Instead of doing everything sequentially, one step waiting on the last, you do dozens of things simultaneously and bring them together at the end. The result is a ship that used to require 4 or 5 years of construction now finished in under 2 years. And critically, the quality doesn't drop. In many ways, it improves because each section can be inspected and perfected independently before it ever becomes part of the whole. But speed and precision in individual sections still doesn't solve one enormous challenge. How do you take over 100 giant steel blocks, each weighing hundreds of tons, and make sure they all line up with each other to within a hair's width? Because if they don't, the whole thing is compromised. That's where China's technology investment becomes almost hard to believe. Across the biggest Chinese shipyards, millions of tiny sensors are embedded throughout the entire construction environment. These sensors feed data continuously through high-speed networks into AI systems that monitor every measurement, every position, every tiny movement in real time. If a section shifts even slightly out of alignment, the system flags it immediately. Not when a worker happens to notice. Immediately. The deviations this system catches aren't the size of a finger or a coin. They're the size of a human hair. And in a structure this large, that level of detection is what prevents small errors from stacking into catastrophic ones. Because errors in assembly don't just stay where they are, they multiply. An error of a few millimeters on section 5 becomes a few centimeters by section 50, and a serious structural flaw by section 100. By catching and correcting them before they compound, this invisible network essentially guarantees that when those blocks come together, they fit like they were always meant to be one piece. Then there's the welding. Every joint on a ship like this has to hold for 25 to 30 years, in salt water, under constant load, through storms, through thousands of tons of shifting liquid, through temperature extremes from the tropics to the Arctic. A human welder, no matter how talented, gets tired. Speed shifts slightly, pressure changes, temperature drifts. Over thousands of continuous hours of welding, even the best human welders produce inconsistencies they can't fully control. So China handed the most critical welding to robots. Laser welding arms work around the clock on steel plates up to 50 millimeters thick. They maintain the same temperature, the same speed, the same pressure for hours, for days, without variation. The joints they produce aren't just strong, they're consistently strong everywhere, every time. There are still sections of the hull, the tightest curves and the most complex geometries, where human experts are essential because machines can't yet match the adaptability required. But by automating the portions where consistency matters most, China removed one of the oldest and most stubborn sources of failure in shipbuilding. The combination of modular construction, AI-guided precision monitoring, and robotic welding isn't simply a faster version of traditional shipbuilding. It is a fundamentally different way of thinking about the problem. And it produces a hull strong enough to carry 2 million barrels of oil across the world's most violent oceans for 3 decades without failing. But a hull is only half the story. What moves it is just as remarkable. The engine room secrets. Moving a 300,000-ton ship across an entire ocean isn't just a matter of dropping in a powerful engine and pointing the bow in the right direction. The engineering involved operates at a scale that most people never think about, and it starts with a fundamental question. How do you generate enough force to push something that heavy, steadily, for weeks at a time, without stopping? The engines used in these ships are 2-stroke diesel engines, built specifically to generate massive force at very low rotational speeds. They don't spin fast, they spin slowly and they push enormously. The scale of these engines is almost absurd when you see them in person. They stand as tall as a 4-story building. The individual cylinders inside them are wide enough for a full-grown engineer to walk into for maintenance. Power output reaches close to 100,000 horsepower. But horsepower alone isn't the point. The point is torque. Steady, relentless, crushing force applied continuously. Each slow revolution of the engine generates a force that travels down a long steel shaft and drives the propeller system at the back of the ship. That propeller weighs over 100 tons and is cast from a single piece of a specialized metal alloy that resists corrosion in seawater for decades. It's made as one piece deliberately to eliminate the joints and seams that would otherwise become weak points over time. The shape of each propeller blade is designed using the same kind of computer fluid dynamics simulations used to design aircraft wings. The goal is to find the precise angle and curve that converts the engine's rotational force into forward thrust as efficiently as possible. Here's a number that shows how seriously this is taken. Improving the propeller's efficiency by just 1% saves up to $1.5 million in fuel costs every single year on a single ship. Across a fleet of hundreds of tankers operating for 30 years, that level of optimization isn't just engineering. It's economics at a scale that reshapes entire businesses. But there's one more challenge that sits between a well-designed engine and propeller system and a ship that actually lasts: vibration. When a massive engine is running at full power and 2 million barrels of oil is shifting inside the hull with every wave, the entire ship begins to vibrate. On its own, vibration is manageable. The problem comes when the vibration frequency of the engine and the shifting frequency of the cargo happen to sync up. When they do, they create a resonance effect, similar to how a singer can shatter a wine glass by hitting exactly the right note. On a ship, resonance doesn't shatter glass, it cracks welds. It fatigues steel. It quietly shortens the ship's life by years. To prevent this, the engine is never bolted directly onto the ship's structural frame. Instead, it sits on a damping system, a set of sophisticated shock absorbers engineered to absorb and scatter those vibrations before they travel into the hull. The result is a ship that runs smoothly even through rough seas and keeps running that way for the full span of its operational life. Now take all of that engineering excellence and apply it to a completely new generation of ships, because China's newest tankers don't just refine what came before. They represent a philosophical shift in what a ship is supposed to be. The Shin Aden is a VLCC with a deadweight of around 300,000 tons. But what makes it genuinely unlike anything that existed before it are the structures standing on its deck. Rigid sails. 40 meters tall, built from ultralight carbon fiber, standing on the hull of a ship the length of 3 football fields, designed not for show but to generate real supplementary thrust from wind. These aren't decorative callbacks to the age of sailing ships. They are aerodynamically engineered structures that capture wind energy and feed it directly into the ship's propulsion equation. Under real-world sailing conditions, they reduce fuel consumption by about 9.8%. That sounds modest until you do the math. On a ship that burns through vast quantities of fuel every day, 9.8% saves millions of dollars per year, per ship. For 30 years of operation, the numbers stack fast. The Yuan Rui Yang takes a different approach but arrives at the same destination. This ship runs on a dual fuel system that can switch between traditional diesel and liquefied natural gas depending on fuel costs, port regulations, and international environmental standards in whatever region the ship happens to be traveling through. It stretches 333 meters in length and 60 meters in width, 3 football fields long, wide enough to lay a multi-story building on its side across the deck. But again, size isn't the story. The dual fuel system cuts carbon dioxide emissions by about 20% and slashes sulfur emissions by up to 85%, meeting the most stringent international environmental standards in the shipping industry today. Standards that most older ships in the global fleet can't come close to meeting. And the newest generation of Chinese tankers is built to last 30 years instead of 25. 5 extra years sounds small in isolation. For a ship carrying millions of barrels of oil per voyage, those 5 years represent hundreds of millions of dollars in additional operating value. For a shipping company that owns a fleet of these vessels, it's the difference between a good investment and a generational one. When a ship is more fuel efficient, cleaner, smarter, and longer lasting than anything the competition can offer at the same price point, backed by flexible financing from state-owned banks that removes the biggest upfront cost barrier, the decision to order from Chinese yards stops being a preference and becomes almost inevitable. And as those orders pile up, year after year, something bigger than a business advantage starts to take shape. Who really controls the ocean? Here's the part that most coverage of Chinese shipbuilding completely misses. The ships are impressive, the technology is remarkable, but the real power isn't in the steel or the carbon fiber sails or the dual fuel systems. The real power is in what all of those ships, collectively, represent in the global energy system. About 60% of all the oil traded anywhere in the world travels by sea. Not by pipeline, not by truck or train, by ship, and the vast majority of those ships were built in China. That single fact creates a direct and permanent link between Chinese industrial output and the global flow of energy. Every barrel of oil that moves from the Gulf to Europe, from the Middle East to Asia, from West Africa to the United States, overwhelmingly travels on a ship that a Chinese yard built. But it goes further than just where the ships were made. When you build the ship, you don't just sell a product and walk away. You create a relationship that lasts for the entire operational life of that vessel. The shipping company that takes delivery of a Chinese-built tanker doesn't just need the ship. It needs spare parts that are designed for that ship's specific systems. It needs technical support from engineers who understand how that ship was built. It needs maintenance services, software updates, and eventually upgrades. All of that comes back to China, over and over, for 30 years. Chinese state-owned banks made this ecosystem even more powerful by fundamentally changing the financial model. Historically, the single biggest barrier to ordering a new ship was the sheer size of the upfront cost. A VLCC costs hundreds of millions of dollars. Most shipping companies, even large ones, couldn't just write that check. Chinese banks came in with financing packages that spread the cost over time, with competitive interest rates and flexible terms that made ordering a new ship far more accessible than it had ever been before. Shipping companies from Greece, Norway, the Middle East, and across Asia started placing larger orders, more frequently because the financial math suddenly worked in their favor. And every one of those orders deepened the long-term connection between those companies and the Chinese shipbuilding ecosystem. Organizations like BIMCO, which tracks global shipping trends and risks, have raised concerns about what this concentration actually means at a systemic level. When the majority of the world's shipbuilding capacity sits in one country, a disruption in that country, whether from trade tensions, natural disasters, supply chain shocks, or policy shifts, sends shockwaves through global shipping that take years to absorb. The dependency isn't just economic, it's structural. But beyond the risk conversation, there's a much longer-term shift happening that deserves more attention than it usually gets. Think about where power in the global energy system has traditionally sat. For most of modern history, it's sat with the countries that had oil in the ground: Saudi Arabia, Russia, the United Arab Emirates, the United States, the nations that could turn a valve and move prices, the ones that sat at the source. But oil in the ground doesn't go anywhere without ships to carry it. And ships don't exist without shipyards to build them. So if you control the means of transport, you hold a form of influence over global energy that doesn't require owning a single oil well. You don't need to be at the extraction end of the chain. You just need to be the one who decides what gets built, how many ships exist, and who can afford to order them. China isn't setting OPEC production quotas. It isn't drilling in the Gulf, but it is building the vessels that carry 60% of all the oil the world buys and sells. And the ships being ordered and built right now will still be sailing in 2055. The infrastructure being created today will define how energy moves around this planet for the next 30 years. It will still be operating when the next generation is making decisions about what comes after oil. That's not a shipbuilding story anymore. That's a story about who holds the quiet levers of the global economy. Not loudly, not through military force or political pressure, through steel and robots, and sails made of carbon fiber, and financing terms that make it easier to say yes than to say no. And when you build enough of those ships, for enough of the world, over enough decades, the ocean starts to look a little different. Less like a natural boundary between nations, more like a network that somebody built and somebody maintains and somebody more and more controls. That's the full picture. From raw steel plates and robotic welding arms to carbon fiber sails and dual fuel engines, China didn't just build the world's largest oil tankers. It built the system that builds them, finances them, and keeps them running for 30 years. And in doing so, it quietly positioned itself at the center of how energy moves across this planet for decades to come. So here's the question worth leaving you with. When the infrastructure that carries 60% of the world's oil is built by one country, maintained by one country, and financed by one country, does that country hold a kind of power over global energy that nobody voted for and nobody can easily undo? Drop your thoughts in the comments below. I read them, and I genuinely love to know where you stand on this. If you found this video worth your time, hit like and subscribe. It helps more than you know. And check out the next video if you want to keep pulling on this thread.